So it was not meant to teach you in depth or to completion a particular algorithm, because in that case we can teach maybe at most say 12 or 20 algorithms, and that's not enough, okay, for you to be a researcher, a capable researcher in machine learning and in deep learning. This class is to train basic people to obtain a research capability as an independent researcher who can develop new equations and the new models and the new techniques. If you want to actually learn how to just implement an existing technique, you can get some training from here, but there are better courses teach you exactly that. So here, why we derive many of the equations as a big homework, for either classical model material is actually meant for training the skill and the way of thinking. And I understand that some of the homeworks may be heavy. Again, we don't have exams, we don't have midterms and finals. It's a trade-off, okay? And also, I think it's necessary to calibrate what do you mean by heavy. About 15 or more than 15 years ago, when I take graphic models from Michael Jordan, it was also complained to be heavy. Many of the students use 5 days to finish one homework problem. Pretty normal. And that's so be it. If you can get 20% of the score, then so be it. That's basically reflecting what it is, right? Because the grading will be curved. Therefore, the absolute number is to inform you where you are. But your final score wouldn't be determined by that, right? So don't worry about the scores and all that. Some people, remember there are famous math classes where the professor is asking students to solve open problems, right? So in that case, maybe no one can solve anything, but it doesn't mean that everybody gets a F, right? So you can still get a pretty good score once you try the effort. So that's basically what the homework is meant to be. It's not for giving you a score. It's for checking your level of understanding and also to practice. All right, so much for, so basically we're still going to cover a number of topics even for the remaining few classes. This very topic, nonparametric Bayesian statistics, could be a whole semester on class, okay? And I originally meant it to be one class. Now I hear that you're concerned about inadequacy of coverage. We may be splitting them into 2 courses, 2 lectures, but no more, because we cannot afford, basically, devoting the entire semester for one topic. We have many other interesting topics. So the main purpose is to open up the literature so that you know this domain and its potential, and then you can follow the reference and some of the classical papers to go deeper and broader into that field. That's what I mean by becoming an independent researcher, okay? More than just a developer. In fact, you are already far more qualified to become a pretty good engineer and a developer in Google and Facebook. And this one is not going to make you a better engineer. It makes you hopefully a better prepared researcher down the road. Okay. So Bayesian nonparametrics, it's a very, very important and once a very hot topic in machine learning. I say once, meaning that now it is not as hot, but I think it's going to be very useful even down the road when this approach is connected to many of the existing technique to further broaden it. For example, in maybe 2 lectures, you will be hearing something called a Gaussian process, which can be applied to deep neural networks to make the layer infinitely wide. How can you come up with an infinitely wide deep neural network if you want to do it and just operationally? Well, it's not possible. But analytically, you can still achieve the effect by using this nonparametric Bayesian technique. So that's actually the beauty of all this technology. They can be connected, they can cross-enhance each other. But let's start from a much simpler problem, which is a classroom problem. I bet this is probably one of the first problems that you run into, in your machine learning, education. And we know a number of algorithms already for this problem, right? For example, k-means and mixture of Gaussian models, right? So you probably learn that from 701, 601, or any other machine learning intra class. And there are also a way to even ask a very, very kind of, I would say, cheap question that could already, maybe confuse or, make the top professors feeling uncomfortable. For example, you can ask how to pick the number of clusters. I often actually see these problems everywhere to challenge basically the lecture. It's a good challenge because there isn't a good solution, but this question exists in every developer's mind. So let's take down this question a little more seriously and see how a nonparametric Bayesian approach offers one of the first principled solution to this. Okay, that's actually why nonparametric Bayesian technique became prominent, a while ago in machine learning, because it does actually give you a legitimate operationalizable solution to this problem. So how to pick clusters? Well, if you have a particular criteria, like for example color, and you are in a finite color space, you can automatically group them with different colors. Right, so that's one way. Or if you ask shape, then maybe there is only one cluster here. Right, so that's where you know a good attribute. But if I take away the attribute and ask you to run a free algorithm purely based on some externally defined distance function, it becomes harder because in here you can see it. So you probably can specify the number to be 3. But what if the data is in a very high dimensional space that you cannot really see how data aggregate? Then setting up the number k becomes a guess. By the way, in that case, what do you usually do? We did teach a heuristic for you to try at least solving this problem. Can somebody try to name a few? Name one at least. It's just try a bunch of k's, right? And then you define some favorite, compactness functions. Say maybe within cluster distances versus cross-cluster distances behaving in a certain way and so forth. There are all sorts of tricks. But this is very, very hard to analyze because that trick usually leads to an objective that is different from the original objective that the algorithm is trying to optimize, such as likelihood of data. Right? And also, the problem can be more difficult if you have streaming data. The data keep coming in, and you really should be prepared for outliers or new patterns. Therefore, the number of clusters may be changing. Old clusters can disappear, and new cluster can appear. And this is very true in news media analysis. You group news documents, and today's topic may become unpopular tomorrow. Therefore, you have to kill that cluster and implement new clusters. And this is actually a very difficult problem. And very often, what people do? Well, people run k-means today, and then people run k-means tomorrow. You have 2 k-means outcome, which appear to accommodate changing clusters because you can set numbers to be different. But then there are also other problems, which is the mapping problem. Cluster number 1 today is not guaranteed to be cluster number 1 tomorrow. Therefore, you need to have this, compatibility, problem to be solved between the 2 clusters, even on the same data, right? Not along on changing data. So let's see how we are going to come up with a better approach. So again, this is the data. In fact, the data here is already a little bit more confusing than the diamond ones I showed before, where the number of clusters are very obvious. But again, anyway, a straightforward approach is to apply a mixture of Gaussian. And this is basically the likelihood function of the mixture of Gaussian over n data points. Therefore, you are going to multiply n times, by the way. n, but it could go to infinity if you have data keep coming in. And within the multiplicand is a mixture model, okay, indicating the cluster label and also the class conditional likelihood of data points. This is known as a parametric model. You fix finite number of parameters, and you are using data to estimate it. Okay. And you can be Bayesian about it, right? Bayesian means that. So by the way, this is a original a graphical model of the clusters. Let's say here, right? So what are these? These are basically the weights of every cluster. You define basically the prior probability of the label. And then this is the centroid and the covariance of one of the k Gaussian mixture components, right? And being Bayesian means that you set a prior for each of that, right? So you set a prior. And typically, you want to use a conjugate priors. And we already knew that the conjugate prior for this one, by the way, is a what? Is a multinomial vector, right? And therefore, the most convenient prior is a Dirichlet prior. And for a Gaussian parameter, which has a mean vector and a covariance matrix, there is also a conjugate prior known as the Gaussian inverse Wishart prior. You can go to the statistical book and check the formula, or go to wiki and find it. It's very hard for me to type those things into the equation, so I just typed the slide, so I just mentioned their name here. And then how to choose the mixture weights. You basically are going to do a maximum likelihood estimation by, say, integrating out those theta and the pi parameters, right? Okay, so this is a Bayesian setting. It still does not solve you the problem of how to estimate this one, k. K is usually not treated as a parameter. It was treated as a tuning element that you can play with. And in fact, one of the key things that determines, that's very relevant to the number of clusters or components, is this Dirichlet distribution. Why? Because it defines the distribution of the weights. The weights actually has to add up together to be 1, right? And therefore, if you divide this 1 more, then the weights will get proportionally shrinked. And therefore, the Dirichlet distribution has to change accordingly. So let's take a deeper look into the behavior of the Dirichlet so that we learn some properties that we will use in the future to develop a nonparametric Bayesian version. So this is the form of the Dirichlet distribution. Okay, it takes an exponential form where you have the hyperparameter alpha. Okay, defining a power of the weights in each of dimension, and then this whole thing in here defined by gamma functions are what's needed to normalize this part so that it becomes a normalizable distribution. And by the way, these coefficients, alphas, are known as the Dirichlet parameters, and they are required to be all greater than 0. Okay. And then the pi's, which are sampled from this Dirichlet, of course, is living in a simplex, meaning that they sum to 1. Okay, and they are each a positive number between 0 and 1. And a physical meaning of these alphas, can be found here. It is the mean parameter. Okay, of remember in our exponential family distribution, we use a mean parameterization. So therefore, here the alphas is also a set of mean parameters for the samples. And depending on the value of the alpha, especially the magnitude of that, you can see the trend of the distribution. Some spread the mass more uniformly, okay, into the whole simplex. Some spread the mass more to the corner, and so forth. And there's a way to also make them a little bit asymmetric like this. Okay, and the Dirichlet is nice because it is conjugate to multinomial. So when you are conditioning on samples x, which are distributed according to the multinomial parameter pi, you actually will get a posterior distribution of the pi, which is also a Dirichlet. Okay, so basically this part, which is the prior, multiplies this part, which is the likelihood of the counts, okay, in the sample. You get a new Dirichlet, which is having a hyperparameter that is combining the prior parameter and the counts. It makes sense, right? Basically, the data becomes part of the knowledge, and therefore you recalibrate the priors. And this is a Dirichlet as well. That's very nice. So now let's see how to use this Dirichlet to. So right now, a Dirichlet distribution only defines, a distribution of the multinomial parameters, and multinomial parameter itself defines, the weights, which is the distribution of a discrete random variable. But you can actually become even more flexible and powerful by using this technique to define the entire mixture model, the entire distribution of the mixture model, rather than just the weight inside the mixture model. Okay, so this is known as a distribution over distributions. How does that happen? So remember, in the mixture model, we have both the weight pi and also what? The mixture components, right? Which is the theta. It is a combination of mu, the mean, and also the covariance matrix, right? And this one, by the way, comes from could be sampled from a Gaussian inverse Weisser prior. For simplicity, let's set this to be constant for now. Okay, just imagine that how we define a prior for this one, for the mu. Again, the argument is generalizable to all parameters, but for the simplicity, we are only going to focus on the mu. So where does mu come from? Well, mu comes from a Gaussian distribution, and it's a distribution over means, just like Dirichlet, it's a distribution over the weights. And how these work next to each other? Well, we first can get the Gaussian distribution to work and produce a collection of the means, which is in here. And for each of these value, which could be a mean of a mixture component, it needs a weight, right? And if we knew the total number of such Gaussian samples already, and we assume each of them is the centroid of the mixture components, then we can define the dimension of the Dirichlet distribution and then sample the weight vector, okay, from Dirichlet. So, so that's basically giving you a mixture model, a finite mixture model in a full Bayesian setting, with both weights and centroids being defined. And what we have is actually a distribution of distributions. For example, here, let's say you have, these three things, which we call them positions. Okay, these are basically the means or the value of the means, for each mixture components. In the one-dimensional case, they are just positions on this line. And then we also associate with each of them a bar whose height is proportional to the frequency of this cluster being used. And this frequency is a component in that weight vector coming from Dirichlet. So these three bars, you can view them as a sample from the Dirichlet distribution, right? And you can do it again and have another three bars which have a different height proportion. They all sum to 1, of course, and then the position are also different. So in this case, you can have many combinations of this three-component mixture model. And a three-component mixture model is a distribution, and what we have now is now a distribution of distributions. right? Again, they are still finite, but that's a good starting point because we at least are coming into a convergence where we treat the definition of the mixed model itself as a random variable. Okay, it's stochastic. Okay, so let's look at the Dirichlet distribution again, so that in the future we're going to use some of the nice properties. Dirichlet distribution is actually very interesting. It has a lot of very intriguing algebraic properties. Without the proof, I'm going to just demonstrate a few so that you can see later on how we can use it. One interesting property of the Dirichlet distribution is called this collapsing property. Okay. For example, if you are going to sample one-dimensional scalars from a gamma distribution, and you basically sample, say, capital K of them, then this, and of course each gamma is parameterized by a alpha, a hyperparameter. Then this vector of gamma variables actually, when normalized, follows a Dirichlet distribution. And the parameters of the Dirichlet distribution is also the vector of the parameters of all these gamma distributions. That's just a very interesting mathematical property. And then, because it is easy to prove that in gamma, if you sum two random variables from two gammas, then the sum of that is also a gamma distributed random variable whose parameters are the sum of the hyperparameters. Okay, so that's a nice property. That means that you can collapse two gamma into one. Okay, and you can use the same trick and now prove that for a k-dimensional Dirichlet distribution, you can collapse them into a k minus one dimensional distribution of Dirichlet by summing the first two dimensions, and then the Dirichlet has a new parameterization for the first two dimensions, which is alpha 1 plus 2. Okay, that's how you collapse higher dimensional to lower dimensional. The other property is the opposite, how you split. Okay, we came up with a k-dimensional Dirichlet. Okay, and let's also sample what we call a split random variable, which comes from beta. Beta is, in a sense, a one-dimensional Dirichlet. Okay, so it has only one hyperparameters, but actually two hyperparameters. So it is going to be defined in this way. Let's split the beta hyperparameter by b and 1 minus b. Okay, b is always a positive number between 0 and 1, and that defines a particular beta where you can sample theta from. Then it turns out that you can use the theta to be a pivot to split one dimension in the Dirichlet, so that this pi 1 gets split into two dimensions. Okay, and then your Dirichlet also has one more dimension, and the first two is actually the original hyperparameter alpha 1, now split it into two by the b1, by the beta parameters. So it's kind of intriguing, right? So the random variable splits the random variable, the hyperparameter splits the hyperparameter, and that basically allows you to now make a even more aggressive split of lower dimensional Dirichlet into high. You can see where I'm leading to. When you split the Dirichlet higher and a higher dimension, maybe at some point it goes to infinity. You have an infinite partite, but you can still analyze it using a limiting case, which gets you back to the finite samples. Okay, so that's kind of the mathematical story behind it. So yeah, so this theta now is no longer from gamma or from beta. It is from a Dirichlet. Okay, and this Dirichlet is now split n way by these little b's. Okay, and then you effectively also are able to split the first dimension of this original Dirichlet also in n ways. Okay, and here is the split on the random variable side, and here is a split on the hyperparameter side, and you basically expand the whole thing into a higher dimensional. Okay, just remember this. By the way, there is also another property called renormalization, which is trivial. I don't need to cover that in detail. You can just read it. These properties will be used in a second to analyze some of the limiting case, okay, when Dirichlet is going to higher dimensional. Now go back to our question, choosing the number of clusters. What does it mean? It means that you have to do something with these priors, right? Here the k should really move to infinity. And here the pi, which is a Dirichlet distributed multinomial vector, it has to go to a infinite dimensional vector so that you can, or at least the unbounded number of vectors. That's the only use infinite because you have finite points after all. Therefore, infinite is just a maybe a vacuous claim. But at least you don't know the number. Therefore, you have to keep this dimension unbounded so that it can fit into any number of data points. Well, this, of course, generates a primarily how to even represent this whole thing. Okay, that's very, very tricky. We're going to find out later how to do that. Okay. Okay, so now before I go to the nonparametric space, let's see the whole picture once more to at least normalize ourselves on the roadmap. So we start from parametric models, which are the most popular and handy models that we use for analyzing data. Clustering data. In fact, it doesn't have to be only clustering. Classification could also, split into the same scenario. And then we actually, in the past, knew some nonparametric models. Some of you guys probably know what is a Poisson density estimator, right? You define basically if you have points in here, and you define a little Gaussian kernel on every point, and you have a window to define the decay of the weights, and you sum all of them together, that gives you a density estimator of a arbitrary data set, right? And basically, you remember all the data points. That's what it meant. That's called a pure nonparametric approach, and it basically allows the number to grow with the sample size, and but it is quite cumbersome and inflexible in many cases to analyze data with very, very strong patterns. For example, if they are not uniformly distributed like this, they do have clusters, then you actually could do better than the nonparametric model. So the Bayesian nonparametric model is also allowing infinite number of parameters in priori because you have a prior. The prior is a space. It is a device define a random distribution on an infinite space of possibilities, okay, of possible cluster centroids, for example. And then the data set that you are going to fit is going to use a finite subset of those parameters. So how to reconcile the infinity and the finite and how to operationalize it? Well, because it's a Bayesian setting, you can very often integrate out, okay, the intermediate layer of random variables, which are the parameters. You can integrate them out if you are using conjugate priors. And then what you are left are only the hyperparameters and the data. You effectively are kind of bypassing the need to specify those infinite or unknown number of cluster centroids or weights. And you can still do inference without assuming the number of data points or number of clusters. Okay, so that's kind of the rationale. The Bayesian kind of vehicle or mechanism allows you to do marginalization of something that is hard to operationalize, and then you are going to really focus on only the more intuitive and direct examples and hyperparameters, but still achieving same statistical effect of infinite modeling. Okay, just let's go to the specific presentation. Okay, so mathematically, it is pretty easy to write. You are going to now use this Okay, you are going to basically include infinite number of components. And you knew that some of them will be used, not all of them, because you have finite data points. But because you don't know, so you have to somehow store it or maintain this list. And how to do that? Well, there are some priors that you probably have to maintain this explicitly, which make it computationally very, very difficult if ever possible. But the Dirichlet process prior that we're going to talk about allows you to implicitly allow infinity, but not necessarily storing or indexing it explicitly. So here's how it works. Let's first make a construction to really understand how you can specify an infinite distribution without writing down an infinite list. Okay. So we start from a two-dimensional Dirichlet, and now we know how to pivot, each dimension and make them into higher dimensional. For example, we can sample a pair of beta parameters, and then each of them pivot one dimension, and then you can turn them into a four-dimensional thing, right? So remember, here you still have just one parameter alpha. You are not actually requiring infinite four parameters or two parameters. You can go on and keep splitting, and at the end of the day, you are going to have a k-dimensional Dirichlet and a k-dimensional multinomial vector parameterized by a Dirichlet that requires only two numbers. One is the alpha, the hyperparameter, which sometimes is called concentration parameter, and the other is the number of components. And of course, as k goes to infinity, you can get an infinitely dimensional distribution of multinomial. Right, so that's actually how you can extrapolate a finite dimensional Dirichlet into infinite without increasing the number of parameters. Okay, so that's the first trick. And then how to turn them into a distribution of distributions, as we liked in the earlier analysis for mixture of Gaussian models. So now you have the weights, which is at least potentially a infinite dimensional weight vector. Then you can always match or accompany the infinite vector of weights with an infinite collection of centroids or positions, which come from say a Gaussian distribution. Let H, for example, be such a Gaussian distribution in a real space. And you can just draw samples from it. Of course, every sample is discrete. It's guaranteed that every time you draw a sample, it will be different from the other one, right? This is the fundamental nature of a continuous distribution. And therefore, you are going to have a set of k centroids. Okay, each of them is corresponding to one dimension or one element in the pi. And then you can combine them together to define a discrete distribution, okay, on the omega, which is just the weight and this delta function, which indicates, correspondence of seeing a particular element, right? If you see a draw theta that is equivalent to this theta, then it becomes 1, and then you have this, right? So that basically defines, the Gaussian is like this. How does this look like? Well, this looks like a set of spikes where the position is determined by Gaussian and the heights are determined by the pi's. And this distribution is discrete. Okay? And you know why this is important? Because if you are going to cluster data around the centroids and you let every time the new data points to choose a centroid in the infinite space, you cannot let them to choose directly from a Gaussian because every time they're going to choose a different centroid. There isn't a clustering effect. But instead, if you let them to choose from here, then chances are they are going to, repetitively choose some points, some, positions to be their centroids, and then you start to see a good clustering effect, right? Anyway, so this construction is called a Dirichlet process because it's defined by a process rather than by a explicit formula. You write an infinite or maybe a very big k number of components and so forth. You write it there and you put it into computer storage. That's not the case. Okay, so here you are basically using a little macro or an oracle that draws samples when needed to ensure the infinite number of components and also their weights. Okay, so this is how it looks like. Okay, samples from that is discrete, and some keywords, these are known, the position are known as atoms or positions, locations, right? And this guy are known as the sizes or the weights. Okay, and again, depending on the value of the alpha, there are different. Okay, oops, the number are missing. There are. I think this is like a small number. This is like maybe a bigger number. This is even a bigger number. That controls you how spread. Okay, this Dirichlet distribution can enable to sample multinomial vectors. Okay, so now let's see some properties of the Dirichlet process. So in a sense, after the Dirichlet process, what you achieve is a partition of the original space. It's discrete, and some particular partite are gathering more mass, and some are gathering smaller mass, and this is actually defined, used to define, the hyperparameters of a Dirichlet distribution. Okay, and the probability of this partition, every partite, is actually defined. By the way, a partition by definition is a vector of numbers between 0 and 1 at 1. It's a multinomial vector, right? And that basically is going to follow this Dirichlet distribution. And it is parameterized by alpha times the base measure. This is called the base measure, okay, defined over the partite. And again, it's a random variable, by the way, so you can have this and that. This is in a finite dimensional, but you can always, split more and more and more, using the same idea, and the formula become the same. It could also, become larger. Like this. Okay. Okay. So this is a finite marginal, which is also a useful thing. For example, if you really don't want to express the infinity of the dimensionality in the partition, you can stop somewhere, say k minus 1, and put all the rest into a tail, and that still gives you, the finite dimensional partition. And then basically, its hyperparameters are now determined by two elements. Okay, one is the concentration parameter alpha, and the other is what is known as the base measure. That's where you actually draw those atoms from. Okay. Okay, so why this is very interesting? First of all, we were able to come up with a process that allows you to, couple a weight vector and an infinite set of atoms, which can be used for many purposes, right? For, say, define the centroid of the clusters. And also, this defines a distribution of the following analytic form when you are able to make a finite realization. And it turns out that this distribution is also conjugate. Okay, the Dirichlet process is conjugate in a sense. What does it mean? It means that if you happen to see a new observation, okay, given that it is in the partite J, for example, then the posterior of this distribution of the partition, the posterior part partition, defined from the Dirichlet process prior, as we see here, and plus one example, becomes also a Dirichlet distribution with slightly changing hyperparameters. And you can imagine the changing is very, very intuitive. It is changed in here, where this part is now collecting one more count, okay, from this observation. Remember, originally we have the partite AJ under the base measure H multiplied by the scale, which kind of gives you the pre-normalized mass, okay, of that particular partite in the prior. And then you see one more evidence, then you add one. That's the idea, okay? And then to make it more general, that's how we write it, okay? It becomes a new Dirichlet process reparameterized by alpha added by 1, and this added by 1, and this collects a delta observation. Okay, so that means it's conjugate. And then also using Dirichlet process, you can define very easy and handy so-called predictive distributions. And that's actually very interesting. Because in here, we still appear to be managing a particular vector of parameters, which is this guy. It is used to really express the posterior. It is really allowing you to have a direct vision about the weights of every parameters. But it's something that is very difficult to manage because you need to. It's a very high-dimensional vector that you have to store it. You actually could use the Bayesian trick to integrate it out and make a sampling procedure a little bit more easy, as you can see in a second. So let's see. Suppose that we want to start from nothing. Let's say just a seeing from the new example. And in here, operationally, you want to start by, a point sampling of a point atom, in the space. And also, we know that before you see anything, and also sampling only a particular atom from the base measure, and the probability of that is under the base measure is 0 because it's a continuous distribution, and you sample from it. The mass of that particular sample is 0, right? But how actually we can really define, the Dirichlet distribution process more operationally easily. Let's look at the first point. So here is how we want to do it. I need to have a singleton, okay, and that's basically, starting from, let's say, an empty space. And my singleton is going to generate, my first example basically is going to generate the first partition. Let's say this is theta 1. And I call everything else to be a null of that. Okay. And then, we need to define pi to be the size of that. Okay, that's basically the weight of the first cluster that you ever need to do. So look in here, instead of as in k-means, I preset k atoms and also k-dimensional weights, and then pull all data in. In here, I already have a different tactic. I'm looking at data one by one. Okay, I'm just looking at one data example. Let's say x1, for example, and I ask which cluster it should belong to, and what weight it should be. Obviously, there's nothing. Okay, you can pick anything to be your cluster center. You can pick anything to be your weight, and that's why we resort to the Dirichlet process to jumpstart this process. So a priori, we are going to assume that this weight and its complement come from this two-dimensional Dirichlet process. Remember, the Dirichlet process is alpha, and we can actually, and here is the weight of the atom, right? And remember, the atom, when plugged into the H function, is 0 if you have only the point mass. Therefore, the first one is actually 0, right? And the other one is basically the rest of the whole stuff. Okay, then, of course, it has to be 1. Therefore, it's 0 and alpha, Dirichlet to begin with. And then I'm adding 1 point in here, and then the posterior, because we assign this 1 point to the first cluster, and that defines basically a new Dirichlet prior, which is now 1 alpha. The thing becomes a little more interesting when you see the second data points. The second data points can have 2 options. It either joins the first cluster, like x1, or it goes to the second cluster, a new cluster, say a new one. Therefore, you need to now deal with a reestimation of the pi and its complement, whether it should go to here and here. And in a Bayesian setting, you can actually integrate out the pi, so that the probability of the p, in the most principal case, you actually, in the most direct case, this x1 equals to theta k should, condition on the pi's, pi 1 and pi 2, and also the centroid, right? So here I'm integrating out this pi 1 because it is conjugate under the Dirichlet process. Therefore, it can be shown that this conditional distribution of the second example, given the first one, can just follow a reparameterized, Dirichlet distribution, which is what we see in here. The posterior of the first one, the posterior after seeing the first example, becomes the prior of seeing the second example. Can you get that? And therefore, when I define the probability of the second example in terms of its cluster assignment, I use basically the posterior from the first example in here. Okay, so that's basically this one. And therefore, this guy has this probability. And then, of course, it defines a new posterior, right, after seeing 2 examples, which actually will go to the next example. So I see the first one. By the way, if we assume that the example 2, x2, goes to a new cluster, then the posterior of the pi becomes what? Let's suppose that this happened. So the second example enters a new cluster. Then I want to ask how does, say, theta 3 look like given x1 and x2? What does it look like? Well, it looks like the following, right? It should be having a pi 1 and a pi 2 and some other things. right? Because you already have two clusters being defined by the first two example, then you need to have a residual probability of the rest, right? So in a sense that if you want to index pi, then every time you need to have a growing list of pi's that is keeping track of the weights of every cluster. But instead, you also could bypass that, because every time you could integrate out pi and only focus on the Dirichlet prior, which is just indexed by alpha, and also the number of clusters you see so far, and also the counts. In this case, if your third example kicks in, and your first two examples are in each one cluster, then you actually have a prior distribution that is 1 over 2 plus alpha and 1 over 2 plus alpha for the two clusters that you already see, plus the residual, that is the remaining probabilities. Right? So this is the prior for P3, and then you can go on and define the posterior of that, and then become the prior of P4 and so forth. So without enumerating too much, you probably can see the following kind of interesting phenomenon, which is that without introducing the pi's at all, because it can be always integrated out, and so that we only worry about the Dirichlet prior and also the sample, you can define this predictive distribution of the label or the cluster belonging of a new data point n plus 1, given the first n data points, in such a way, which is a multi-way distribution where, suppose these first 1 to n class data points are now falling into k bins. Okay, they pick up k items, and then for each k items, there is a count of m, meaning how many samples are picking that item. You just index that, and then they basically, each, defines a weight of mk over n plus alpha. That's basically, all the clusters that has appeared already in the previous n-1 examples. And then there is a residual probability, okay, of picking yet another new cluster, which is defined by alpha over n plus alpha. Okay, so what's the moral here? The moral here is that you can keep attributing the label of new data points purely dependent on all the old data points, in particular the counts of them. And also a alpha, the concentration parameters inside the Dirichlet distribution. Therefore, the pi's are not needed, they are integrated out. Okay, so this is called a predictive distribution, which is actually a marginal, okay, of the assignment of the new data points given the old ones, and also the prior. And this is particularly easy and particularly operationally easy, because it allows you to avoid sample very complicated continuous random variable like pi, right? And only basically worry about the data points. There is a nuance that I didn't mention, which is that how to determine this, because here we are talking about sampling exactly the atom itself. But in real example, you are grouping real data points around the atom. There is another step that you need to take care of, but we're going to discuss that in a second. So are you still with me right now? Of this, I try to slow down a little bit so that you know this construction, of a label assignment in a nonparametric case. So this is the kind of the signature of a nonparametric technique, that you really use the data to determine the number of parameters and the distribution, and you not pre-specify dimensions and all that. And also the data is really coming in, one after another, rather than once for all, in a single batch and with a preset placeholder of the model. Okay, there is no placeholder in here. Yeah.
Sorry, how we discuss how to pick alpha?
How to what? Pick alpha. Oh yeah, good point. You guess. Sorry. Yeah. So again, there is no free lunch. There is nothing 100% automatic. You have to make a judgment, on something. In here, you at least should pick one number rather than many numbers. And alpha has this general property, as I said. If it's small, it appears to encourage concentration of a few clusters. If it's big, it allows to spread and so forth. But typically, people try a few things. Yeah. So yeah, you're right. In fact, one of the major attack or objection to Bayesian nonparametrics that say, yeah, I don't pick K anymore, but I pick alpha. What's the deal? Well, sure, right? But here, at least the alpha is easier to pick, and also it does allow more flexibilities, in trying the sampling procedures like this, because it's incremental, right? Okay, so I'm going to now go back to some historical aspects about the Dirichlet process on how they are invented. The Dirichlet process or its analogs have been invented and reinvented many times, in different contexts, and I think it's a very interesting convergence in the end that you can see. Let me tell you a few stories. They are basically the stories used in the early 70s and the 60s to motivate such a construction. So one very well-known process or construction is known as the Poyer-Erm process. Okay, it says the story goes like following. Okay, you have an erm which is either empty or having a few balls inside it. Okay, and the ball has are colored. And then the process goes like you are going to draw, from the ball from the urn a ball, and you can imagine that the probability of the ball of drawing a particular color is proportional to the number of balls belonging to that color, right? So it basically follows this probability because, you can, if you draw a ball with a known color, you basically are going to add, one ball back to the urn with the same color. You have a residual probability of drawing a new color and pick a new ball into that. Okay, and you continue this process on and on. It turns out that this whole joint distribution of the color partition is a Dirichlet process. Did you see the similarity of this to what I just said? Right? Somehow there is a gets richer kind of effect, and also there is a adventurous effect that you can still try new things, but existing patterns are to be reused depending on its popularity. Okay, so this is called Poyer-Erm, and I have a verbal description in here. And then the other one is known as the Chinese restaurant process. It's kind of a better known name maybe in machine learning because I think it is a little bit more intuitive and fun, to communicate. Same thing. Okay, this guy walks into a. By the way, the origin of the Chinese restaurant process has even more nuance in that. For example, why the table is a round table rather than a square table, there are subtlety in there. We're not going to discuss that. Again, we machine learning people sometimes are not having patience to dig into these irrelevant details. Irrelevant means that they are not so influential, impactful on our applications, but they do have very interesting mathematical effects, such as ordering and exchangeabilities and other things. Anyway, just focusing on the grouping effect. Here is what happens. A customer walks into a restaurant, a Chinese restaurant. The way they think about Chinese restaurants is that they seem to be mysterious. An infinite number of tables and the infinite number of dishes can be served. and people come in and sit on this round table, okay, and he will sit there, and then the second customer will come in and he will do the following. He will look at the configuration and try to sit to a table that is proportional to its popularity. The more people there, the more he wants to join. But of course, also with a residual probability alpha over 1 minus n plus alpha, he's going to pick a new table. Okay, so there are some kind of eccentric people who are allowed to pick new tables. And at the end of the day, you can measure or count the number of customers around all tables. And again, that partition is a Dirichlet process. Okay. I didn't say one more thing, which is that what do they do? When they sit on table, they need to eat, right? So in fact, they're going to sample a dish for that. And that's basically where our base measure came in. The dish actually can sample from a base measure, such as a Gaussian. And these guys will share a particular Gaussian mean, and this guy will be sharing a new second Gaussian mean, and so forth. And that's basically how you can come up with a clustering effect. And also, that's how you can cluster these clients without pre-specifying the number of tables and without pre-specifying the weights on each table. You just let basically data walk in and define their affinity. In fact, in here, the affinity becomes a little bit different. Not only the affinity is determined by the number of clients on the table, which purely is a rich gets richer effect. The dish also kicks in. How much I like the dish. The multiplication of these two determines together whether he sits on table. So that makes more sense, right? So that's actually how a clustering could happen. How close I am to the centroids, okay, is one of the factors determining whether I should join a cluster or not, in addition to its popularity. Yeah, but again, you could still join a very popular cluster even if the centroid is a little bit far away from you. So that's kind of this trade-off between the rich gets richer self-reinforcing effect versus the alignment effect on centroids is naturally realized now in this setup. Now you may ask, it looks like there is a flaw there, right? All I said is starting from data 1, and then I ended up like data n. Then they group together and so on and so forth. What if, but you can say, I'm going to cluster this whole thing, and I knew it ahead of time already, maybe. And then what if I choose a different order of the data points? Are they going to define a different partition? That's a problem, right? If the same data set, depending on the way you use the data set, leads to different cluster results, that's undesirable, right? Okay, it turns out that you can prove a important results if your prior is a Dirichlet process, which is known as the Dirichlet theorem. Okay, it says that if a sequence of observations, okay, is exchangeable, there must exist a distribution given which they are IID. Now goes back to our original construction of the Dirichlet process, where we didn't integrate out the theta at all. You can notice that the way I draw the theta and the pi is a IID process. Okay, so the Dirichlet process, the samples, basically samples from the Dirichlet process is IID. And you marginalize out those pi's, the weights, then you cause a sequence effect that the next example depends on the previous example. But if you introduce them back, which does not change the model, okay, it's actually giving you IID examples of the centroids and also the weights. Okay, therefore, in this detour, you can prove that the grouping that I just mechanism I just presented is actually not dependent on the ordering. Because what you do in the actual calculation in the inference algorithm that you need to keep resampling. After all, you need to estimate the theta, the pi, and also the centroids according to data. And one round of sampling is not important, because once you assign the cluster and you redo it again, just like in k-means, your first iteration groups your data points into centroids, and then your position of the centroids actually changed, and then you regroup it. Same thing in here. You are going to resample. Therefore, even though you use the same ordering, once you sample them infinite or many number of iterations, it gets to a partition and the assignment independent of the ordering of your samples. Okay, and theoretically, it's guaranteed by the definity theorem. You have a prior generating IID examples of the parameters. I have 5 more minutes just for fun. There is another process that is also leading to an equivalent of the Dirichlet process. That's the third thing. We have the theorem, we have the Chinese restaurant, and we have the stick breaking process. And this is how it goes. This is more close to how we construct the distribution in the first place. Let's imagine I have a stick of a unit length 1. Okay, and I have a base measure, which in this case a Gaussian. Then I run 2 parallel processes. One is called stick breaking. I'm going to draw a random beta random variable. Remember, beta random variable is a random variable between 0 and 1. It's a pivot basically to a unit length, right? So I'm going to use the beta to pivot this unit bar, and I'm going to define the whole one of the fragment to be my pi, my weight. And accordingly, I'm going to sample an atom from the base measure, and that forms a pair. And then I'm going to pick the remaining, okay, and reapply a pivot that is coming from the second beta parameter, and that gets me another pi, and then I get another atom onto that. I can do that on and on. And you can imagine that this process is infinite, right? Because I can always go to an infinitesimal small length of the stick and keep breaking it. It's kind of becoming philosophical, but in theory, you can never stop, right? And then you can accordingly draw the atoms. And it turns out that the resultant collection of the pi's and also the atoms follow, again, a Dirichlet process. So what's the virtue of that? The virtue of that is that, first of all, it is a Dirichlet process magically. They are the same as the partition generated from the theorem. But in here, it gives you some intuitive information that is of operational value, because you can see that somehow there is a tendency of the stick to be smaller and smaller. It means that there is a ordering defined by the priority or the mass of every partite, and it doesn't mean that your new clusters are smaller and smaller. It doesn't mean that. Okay, so this is a prior process which for you to define all partitions once for all before seeing any data yet. Here there's no data. Okay, but because it is equivalent to Dirichlet, you kind of can imagine that even among Dirichlet process, there is a priori a ordering of all the weights. Some are bigger, some are smaller, and this stick breaking process allows you to come up with a sampling scheme where you can truncate and find an approximation to the Dirichlet process in a finite dimensional space. If your bar is already too small, you could ignore it and start turning back to the finite dimensional process. Okay, so yeah, so this is come up approximated by a finite dimensional prior, but this finite dimensional is not specified by a guess of k. It's by stick breaking, keep breaking until you see it is really too small and you stop. That's more kind of intuitive and convenient than actually guess a k before doing anything, right? And that's actually the backbone of one of the sampling algorithms used in in the Dirichlet process. Okay, so we're almost out of time, but now go back to maybe a summary before I leave to the next, my student to lecture the next set of the notes. What we have is basically, a nonparametric Bayesian upgrade of what was already originally a classical graphical model, right? So here, originally we have this part of the graphic model as a finite kind of mixture model. Again, in the Poisson expression, you use this mysterious G to define a Dirichlet process, which is the distribution of distributions. And this G is defined by alpha, the scaling parameter, and also a base measure, that's where you draw the atoms. And then, from there, you have this infinite cluster that defines the centroids and also the positions of the samples. Equivalently, the Dirichlet process, the stick-bring process is a little bit more intuitive, which is that this G is now explicitly split into a weight vector and a position vector, a position collection, position set. And this one is by a stick-breaking process. That sticking process is to use a beta variable to pivot the stick. And the alpha actually is the parameter in that beta distribution. It's kind of magical, right? And then this base measure is again used to keep drawing, atoms to define the centroid of these guys, right? And therefore, you can see the graphic model here is a little bit different. Here I introduced this labeling variable y, which is the label of the x on a particular cluster assignment, and the label follows a multinomial distribution of weights. Right. Here I didn't do the weight. Basically, it is kind of intuitive from here to here. Y x picks a particular. Basically, it means that every x has its own centroid, but this centroid under Dirichlet can be repetitious, because in the Dirichlet you have a discrete set of centroids. When every x comes in, they can repick a centroid. Okay, so here you can see the number of parameters in here appear to be more than what I have here. Here, theta is into, say, k, and here the theta is only as many as the number of examples. But in essence, they are the same, okay? Because in here, I allow repetitious, or identical theta to be drawn from the Dirichlet process prior distribution. Okay, I think I should stop here. And next, we're going to discuss. In fact, the inference algorithm is pretty trivial. You basically can, allow every example to, come with a label z, and then, the label z is determined by, again, very intuitive functions. It is by this guy, which is the count that we already mentioned about, right, for this rich gets richer effect, or this residual kind of factor allowing to draw the new cluster, and also the likelihood of this data point under the corresponding centroids. Okay, so these two things together determines the likelihood of a particular new data point being assigned to a particular either new or existing clusters. And of course, this probability of a new cluster has to be a little bit more complicated, where you need to define the likelihood of this data point under the base measure, and also the likelihood of the data point given the parameters drawn from the base measure, and you integrate out these parameters, right? Marginal likelihood of the data under base measure. All right, so this is called the collapse skip sampling, because this part has been collapsed out, okay? And of course, the pies are also collapsed out. There are some problems that you can take a look by yourself. And the next time, Marwan is going to talk about a fancier version of the Dirichlet process under topic model, which allow you to grow the topics into infinity, so that you don't have to pre-specify the numbers ahead of time. It's quite an interesting model, but I don't have time to cover it by myself now. Okay, see you next time.